let's talk about the triangularity of the Kostka matrix. So recall what are the Kostka numbers. So we said if you write a given complete symmetric polynomial h lambda in terms of the sure polynomials s mu, so I'm suppressing the variables x on both sides. What you get is the Kostka number k mu lambda. Okay, so this is the sum over mu. So what are these here? So let's take mu and lambda just partitions. So let's just say lambda is a partition, lambda 1, lambda L, and of D, maybe let's say lambda is a partition of D, and the sum here ranges also over mu over all partitions of D. Right? In fact, if you have some n variables, then you can think of both lambda and mu as running over partitions of D with at most n parts and so on. Okay, now what I want to do is to think about what it means for a certain S mu to occur in this expansion. In other words, suppose this coefficient k mu lambda is positive, then what does that tell me? Okay, so let's ask ourselves that question. So question, if the Kostka number k mu lambda is strictly positive, then what can we conclude about lambda and mu? Now, what does this mean by definition? This means that there exists at least one semi-standard Young tableau whose shape is mu and whose type is lambda, right? So observe, this means the following, at least that the set of semi-standard Young tableau of shape mu and type lambda, this set is not empty, right? So in particular, there is at least one semi-standard tableau. So what is a semi-standard tableau? So recall, what that involved was trying to fill. So let's say I have the shape of mu. This is the Young diagram of mu. And what you have to do is to fill these boxes with, so when you say the content is lambda, that just means you have to fill the boxes with lambda 1 1s, lambda 2 2s, and so on. So let's say this shape of lambda. So I need to write lambda 1 1s somehow. So fill with lambda 1 1s, lambda 2 2s, etc. Okay. Now where will the ones go? The ones go somewhere. Now in such a way, remember the filling is supposed to satisfy the semi-standardness condition. So the entries along the columns have to be strictly increasing, the entries along the rows have to be weakly increasing. Now that condition implies the following, that where can the ones possibly occur? All the ones have to occur in the first row. Okay, why is that? Because if it occurred in some other row, then the entry on top of it, okay, recall along that particular column, you must have entries which are strictly increasing, and that wouldn't be possible, okay, if one occurred somewhere in a row other than in the first. Okay, so all the ones are in the first row. Okay, good. Now where are the twos? Well, the twos can either be in the first row or in the second. Okay, I mean, recall this is sort of also how we constructed this tower and so on. So the twos can only be in the first or second rows, also from the semi-standardness condition, right? For the same reason, if a 2 occurred in a third row, then there are 2 entries above it, and you couldn't possibly satisfy strictly increasing in that way. Okay, the 3s can only occur in the first 3 rows and so on. So what this says is that so the strictly increasing condition imposes a certain restriction. So we conclude the following: the numbers 1, 2, 3 till I. Okay, look at the numbers from 1 to I. These numbers can only occur in rows 1 to I. Okay, in other words, I cannot occur in row I plus 1 or beyond. Okay, so this is the simple observation. Now what does this mean? Recall there are supposed to be lambda 1 1s, lambda 2 2s and so on, right? So how many of these numbers are there? The numbers from 1 to I. Well, there are lambda 1 1s, then there are lambda 2 2s, all the way to lambda I i's. Okay, so this is the total number of boxes which will get filled with numbers from 1 to I. And observe that these boxes should all occur only among the first I rows of this shape mu, right? So recall this outer shape is the shape mu, and so that means that these number of boxes, there must be at least mu1 plus mu2 plus mu1 plus mu2 plus mu I, the total number of boxes in the first I rows of mu must be at least this number. Okay, so this is the condition. Okay, so observe the number of ones, all the ones occur in the first row, so the number lambda 1 can be at most the size of the first row. Similarly, 1s and 2s can only occur in the first two rows, so lambda 1 plus lambda 2 has to be less than or equal to the size of the first row plus the size of the second row, and so on. Okay, so this is sort of a necessary condition. Okay, so we conclude that the following is true if the k mu lambda is positive, then this condition here holds for all I. Then summation lambda p from 1 to I is less than or equal to summation mu p Okay, and for what i's is this true? Well, if you sort of see what, how do we apply this? This is for all I going from 1, 2, 3 till L, right? L is the length of lambda, if you wish. Okay, now let's make a definition here. So observe that, maybe this is already starting to worry you because see, length of lambda and length of mu, I didn't assume anything about them to start with. But when I say this, on the right hand side, I may not be able to talk about the part mu p if p is bigger than the length of mu. Okay, so that may be a worry. So what we'll do at this point is to say, okay, let's just assume you put zeros to the right of both of them so that they are both thought of as having the same number of parts. Okay, so let me just say for now, note. Okay, for this to make sense, if length of mu is less than the length of lambda, then pad mu with those many zeros. Pad it with, I should say, pad mu with zeros, so that the lengths are the same. Okay, so that let's leave it at that. So you just put in those additional zeros so that they both have their vectors of the same length. Okay, but you'll see in just a moment that that case is never going to arise. Okay, good. So this is just to ensure that the definition is clear. Now let's just make a more formal definition here. So definition. Okay, so we say given two partitions of the same number, so let mu and lambda both be partitions of the same number, we say that mu dominates lambda, so it's going to be a partial order, dominates lambda, and we write this as follows: mu is triangle lambda, mu dominates lambda if the following holds. If what we wrote out already, summation lambda p from 1 to I, 1 to I for I equals 1 to so let us say, let's put I equals 1 to n, and where we can always pick n to be bigger than the lengths of both of them. Okay, for any n. Length of lambda and length of mu. Okay, and what is the meaning of this? You just put zeros at the end of both mu's and lambdas so that they both have length n. Okay, so I'm making both of them of the same size so that I can do this comparison a bit more clearly. Okay, and the definition doesn't really depend on the n as well. So let's just look at the following example. So if I take mu to be the partition, let's say 5, 3, 1, it's a partition of the number 9, and if I take lambda to be the partition 4, 2, 4 plus 2 is 6, plus 2 is 8 plus 1, 4, 2, 2, 1. Okay, look at the partition mu is 5, 3, 1 and lambda is 4, 2, 2, 1. Now, in order for me to apply the definition, so what am I supposed to do? I just have to see, okay, is the first part of lambda smaller than the first part of mu? Okay, so 4 is smaller than 5, so that's all right. I have to compare if the sum of the first two parts of lambda is less than or equal to the sum of the first two parts of mu. So 4 plus 2 is indeed less than or equal to 5 plus 3. Okay. Now the sum of the first three parts of lambda and the first three parts of mu. So that's 4, 2, 2, which is 8. And mu is 5, 3, 1, which is 9. Okay, now observe this has already reached the maximum. This is both were partitions of 9 to begin with. And now I look at lambda 4, 2, 2, 1, which is 9. And in order to compare, in some sense, what I should do is I should just pad mu with a 0. So I'll just put a 0 there just so that I can compare. I have one more component to work with. So this is a 0. Okay, now let's compare. So this is of course 4, 2, 2, 1. 5, 3, 1, 0, just 9. And at this point they're actually equal to each other. Okay. So this is an example of a mu which dominates lambda. Okay. Now observe that, I mean, the way I defined it by saying, okay, just pad zeros, whichever one has fewer parts, you put zeros at the end so that you can compare. So here's the simple observation. So let me just say a few simple observation facts. 1, mu dominates lambda, then mu always has smaller length. Okay, this is sort of easy to see just from the definition, because remember they are both partitions of the same number. That's important in this case. Okay, so if mu had more length than lambda, then when you keep doing this process of taking the first few parts of first I parts of lambda and the first I parts of mu and comparing, when you keep doing this, lambda cannot get exhausted first before mu. Okay, if that happens, then the total sum of the parts of lambda would have already been the maximum. Okay, and that would beat the sum for mu. Okay, so when you do this process of comparing, you should exhaust mu before you exhaust lambda. Okay, or they could both get exhausted at the same point. In other words, their lengths are the same. Okay, so this is first fact. Fact 2 is that the partition. So I assume throughout that they are both partitions of D, right? So there are two obvious partitions. So one of them is just the partition D is bigger than lambda for all lambda partitions of D. So this is the maximal guy. Okay, D, single part D. Okay, why? Definition. Mu gets exhausted just in the first step, and therefore it beats every partial sum of lambda. And what's the smallest guy? Lambda beats the partition, is lambda dominates the partition 1, 1, 1, 1, 1 D times. Again, for all lambda in partitions of D. Again, why? More or less definition. Okay, this is 1, 1, 1 is the one which gets exhausted at the very end. You have to keep taking all the terms. But if lambda is not equal to this, then it will, at every step, lambda, the sum of the first I parts of lambda is at least I. Okay, good. So this is the maximum and the minimum with respect to this order. So you can check this is a partial order also. So that's the other important thing. This is a partial order. Okay, it satisfies the transitivity property in particular. Okay, good. And there's one more interesting statement about this, which is that if mu dominates lambda, then when you conjugate it, so recall the conjugation of the partition, then lambda prime dominates mu prime. Okay, so conjugation changes the order. So it's sort of like negation in some sense for the usual partial order. Okay, good. So these are 4 easy facts, which I'm just going to leave the proofs as exercise. So they're all easy just from the definition directly. Okay, maybe the only thing you have to think about a little bit is the last one. Of course, all this definition of dominance and so on was inspired or motivated by our study of K mu lambda, the Kostka number, right? So recall also that if the Kostka number is positive, then what we observed was that mu had to dominate lambda. Okay, so this is another nice fact, important fact. And here's an additional. So if mu equals lambda, so by the way, when I write this symbol, dominance, what I also mean is greater than or equal to. Okay, so we're not going to write that all the time, but what this means is that it dominates, and of course the definition of dominance also includes a case when they are equal. Okay, now fact 2, K lambda lambda is 1. Okay, now why is this? Because what does this mean? This says you have to try and manufacture a semi-standard Young tableau whose shape is lambda and whose type is also lambda. Okay, now what does that mean? You must try and fill the shape of lambda with lambda 1 1s, lambda 2 2s, and so on. And we already saw the 1s can only occupy the first row, right? And there are already lambda 1 1s, which means the entire first row is occupied. Okay, 1s and 2s can only occupy the first 2 rows, and there are lambda 2 2s already. So the 2s occupy the entire space available. Similarly, the 3s can only occupy the first 3 rows, and there's only that much space available, and so on. So if the shape and the type are the same, then there's really no choice. Okay, all the 1s must be in the first row, the 2s in the second, the 3s in the third, and so on. So in other words, there's just a unique semi-standard tableau of that shape and type. Okay, so it says that K lambda lambda is actually a 1. Okay, good. Now let's come to the theorem that uses this observation. So this observation, the thing that I just wrote out, is what's called the triangularity of the Kostka matrix. It actually turns out that the converse is also true, in the sense that if mu dominates lambda, then K mu lambda is also positive. But we are not going to use that for what I'm just about to say. Okay, so I'm not going to worry about this just right yet. Now here's the theorem, which says that the H's and the E's that we constructed, the complete symmetric polynomials and the elementary symmetric polynomials. So now this, I'm just going to index it by the conjugate. It's for convenience. Lambda 1, lambda 2, x1, x2, xn. Again, here lambda belongs to. Both of these form bases of the space of symmetric homogeneous polynomials in n variables of degree d. Okay. So observe, we've already constructed 2 different z bases. One is the monomial symmetric functions. The other is the Schur polynomials. Okay, now we have 2 more, the h lambdas and the e lambda primes. Okay, the conjugates. Okay, let's prove this. We already have all the ingredients required to prove this. So when you already know certain bases, and you have a new set which you want to show as a basis, all you have to do is to just show that the new set can be expressed as some invertible matrix times the old basis. Okay, and that's really what we'll do. We already know what that matrix is. If you want to express an H lambda in terms of a known basis, okay, in this case I will use the basis of sure functions, we know what the coefficients are, we know what the transition matrix is. Okay, so which is k mu lambda. So observe that. So if I restrict attention to n variables, lambda x1, x2, xn will just be k mu lambda times s mu x1, x2, xn. Okay. Now, so what does this mean? So this is for all lambda. Okay. Now, why is this? In the sense, if lambda is in PDN, then why should mu only range over elements of PDN? I can actually do better. So let's use what we have just learned about the dominance order. So I pick a lambda from PDN and I ask what are the possible terms that can occur on the right hand side. Okay, what are the mu's that I can get? Now what I already know is this: if a term mu occurs with a non-zero coefficient, then that mu necessarily dominates lambda. And we have just shown that dominance has the following property, has the following consequence, that the length of mu has to be smaller than the length of lambda. Okay. In particular, so what does this mean? So in fact, I can just do this. Instead of summing over all possible mu's, partitions of D, it's enough to just sum over those partitions which dominate lambda. Okay. And of course, as we just observed, this automatically means that mu also has at most n non-zero parts. Okay, because dominance implies that the length is smaller. Okay, good. So what this means is that if I restrict attention to the lambdas in PDN, then the mu's which occur in the summation are also in PDN. Okay, so I can now form a matrix. So I can think of it as follows. So let's do that. So so maybe we should, just from a usual matrix notation perspective, let's just arrange the set PDN, the elements of PDN as follows. So let's do this. Let's write PDN as lambda 1, lambda 2. Maybe lambda 1, lambda 2 is suggestive of the parts of lambda. So I'll just make it superscripts. So lambda superscript 1, lambda superscript 2, and so on. So these are the elements of PDN just arranged in some order. Okay. Now, when I arrange them in this order, I also want to ensure that this arrangement respects the dominance order, such that if a certain element is dominates another, if lambda I dominates lambda j, then we ensure that we list I before j. Okay, if lambda I dominates lambda j, then we write I before j. Okay, so dominates and not equal. Okay, so I'm just trying to list them in a certain order which respects the dominance order, the partial order. Okay, how do you do this? For example, this just says that the very first guy, lambda 1, has to be the maximal guy in the dominance order. Okay, in other words, this must be the partition D. The last fellow should be the partition 1, 1, 1, 1, 1. Okay, I mean, depending on whether the number, whether that last part has at most those many variables or not. Okay, if not, you'll pick the smallest one which satisfies that property. Okay, if there is a unique smallest. So and then how you will arrange them is sort of in you look for the next maximal guys after D. There may be several of them. You list all of them one after the other. Okay, and then you sort of go down level by level. So this is something that can always be done. Okay, that when you have a partial order, you can arrange those elements in a linear sequence. This is sometimes called a linear extension of the partial order, such that whenever lambda I is bigger than lambda j in the partial order, then I comes before j. That is, lambda I is listed before lambda j in this sequence. Okay, now I arrange it in this order, and once I do this, I can talk about the K matrix. Okay, so what's my K matrix? So let me define Kij now. This is just the Kostka number K for the pair lambda I, lambda j. Okay, maybe I'll put some funny script notation here. Script Kij is just the Kostka number K lambda I, lambda j for I and j running from 1 to n. So I formed a matrix, and why do I want to do this? Because now observe that the equation that I wrote earlier, that h lambda, okay, equals summation k mu lambda s mu, I can think of as follows. I will just change my lambda to a lambda I, my mu to a lambda j. So let's redo this. So let me call this lambda I, sorry, I on top. And I will change my mu to a lambda j. So I've done nothing. I've just changed mu to lambda j and lambda to lambda I. And this is now some j going from 1 to capital N. Okay, so this is true for every I. So this is true for every I from 1 to capital N. So this is exactly the matrix form, right? So this is just saying, if I write H as a vector, if I list H lambda 1, H lambda 2, etc. So lambda n, then this is nothing but this is the K matrix, right? So this is summation. So that's not right. The summation again. This is the jith element of the script K matrix. In other words, I have to look at the script K matrix and take its transpose. So take the script K matrix that I wrote out, take the transpose of that matrix, and then times the Schur function vector s lambda 1, s lambda 2, s lambda. So this is just a matrix way of writing that equation that we had earlier, okay, the one we have above. Okay, so the vector of h's is K transpose times the vector of s's, and therefore if you show that the script K matrix is invertible, then we are done. Okay, but observe, it's even better than invertible. We've just shown the following, that the K matrix, so what's the ijth element? Recall, it's K by lambda j. We already said K has the following property, that K lambda, K mu lambda is positive, implies that mu is bigger than lambda. Okay, and also that K lambda lambda is 1. So what does this mean? That in terms of I and j, so recall, this just means that Kij. So what property did we have? We said that if lambda I is bigger than lambda j in the dominance order, so maybe we should just do this. So K lambda I lambda j, the Kostka number is positive, implies lambda I is bigger than lambda j, and this means that I occurs before j in our ordering. Okay, what does that mean? This means that if this entry, this is the script Kij entry, right? So if script Kij is positive, then this is, the Kostka number is positive, then it implies that I is less than j. So what does it mean? If you look at what the script K matrix looks like, if it has a positive entry, that entry only occurs when I is less than j. Okay, and further, the diagonal entries are all 1. So the diagonal entries are 1, and where do the non-negative entries lie? So observe, these are positive is also same as saying non-zero. The only non-zero entries can occur when I is smaller than j. In other words, it's under the diagonal. Okay, everything above the diagonal is actually a 0. Okay, so these are all. So observe, these numbers are either 0 or positive integers, strictly positive. So the script K matrix is actually lower triangular with ones on the diagonal. So it's lower unitriangular. Therefore, of course, it's invertible. Its determinant is exactly 1. So it's invertible over Z, right? So it's actually invertible over Z. In other words, the inverse matrix has all integer entries. Okay, now that's all you need, because if you go back and see what it implies, the H vector is K transpose times the S vector, and K transpose is also invertible. It's now upper triangular. Therefore, since the S's were known to be a basis already, the H's are also a basis. Okay, so since S lambda I basis, so is okay. Now the proof for E is very much the same. It's just apply the other equation. So let me just quickly tell you what one does for E. Okay, so I'm just going to take E lambda prime, and if I see what I'll get on the other side, the matrix, the transition matrix, the entries are K mu prime lambda prime now. Okay, so that's my new matrix. So earlier I had the script K matrix. This new matrix is, maybe call it script K bar. You see what is its ijth entry that we are interested in. It's not, it's the Kostka. The earlier guy was lambda I lambda j, but this guy is lambda I prime lambda j prime. Okay, you take the conjugates of those guys. And this is the new matrix you need to look at. So K bar, and then again show similar facts about it. K bar is, so recall we had this earlier fact which says that if lambda dominates mu, then so we have to use a statement about dominance order that one had proved earlier. This means lambda prime is dominated by mu. Okay, use that to show that this matrix K bar is also triangular. It's also upper or lower triangular, to show K bar is triangular matrix with ones on the diagonal.